Hello, my name is DeepVed, and in this project, I've explored how we can use machine learning to predict the electrical energy output of a combined cycle power plant. It's really interesting data set because it reflects real operational conditions, and the goal is to see which model can give us the most accurate predictions. S- Let's jump into it. So here's the big picture. We have the data set 9500 plus hourly observations, four environmental features: temperature, vacuum, pressure, and humidity. And our target is net power output in the megawatts. So let's dive in. Uh, Before jumping into the model, I will spend some time understanding the data. The distribution looked clean, no missing values, and everything fell within realistic ranges for the power plant. That gave me the confidence that I could move straight into analysis without having heavy processing. Um, so when I looked at correlations, two features immediately stood out: temperature and exhaust volume. Both showed a strong relationship with power output. Temperature specifically had a strong negative correlation, which makes sense because high temperature reduce turbine efficiency. This These are the early signs helped me anticipate which models might capture the patterns better. But we'll see in the future slides how I've used different models to compare. So when I've plotted these feature against the power output, the relationship weren't perfectly linear. Temperature and vacuum had a clear non-linear pattern, if you see here, and that was a hint that some linear regression might not be enough, and we need to have to go to some flexible models that could perform better. So here's what we did for the modeling process. I split the data, standard thing that was taught in the training. Split the data into training, validation, and test sets. I use the cross validation on the training sets so each model can be evaluated fairly. Then I trained six models: linear, polynomial, ridge, lasso, random forest, and gradient boosting. That gave me a good mix of the simple, regularized, and ensemble based approaches. So we'll see the comparison in the future slides. So if you look, I got the R square score for each of them. The models did okay. They captured the general trend but missed some of the complexity. Polynomial regression helped a bit, but the real improvement came from the ensemble model. So if you see, random and forest and gradient boosting both performed extremely well. And in the future slides we'll see the more comparison. But overall, this slide and this slide kind of gives you a very high overview of how the you know how the random and gradient boosting both performed extremely well. It achieves R square of 4.96, RMSE 3.25 megawatts. This means that the model's prediction are actually within the 3 megawatts of the actual output, which is very accurate for the kind of the system. Um, right. So going forward, this table, I mean, these two are more for the um, you know understanding the different models and their R square, RMSE, MAE, and MAP model. So this comparison kind of shows you um, the clear winner here, and you can see that the random forest came out to be pretty good. So then I kind of, when I looked at the predictions versus actual values, the points line up almost perfectly along the diagonal. That's exactly what you want to see. It means that the model generalizes well, and this is not just memorizing the training data. So the residual plot backs this up. The errors are small, evenly spread, and don't show any obvious pattern. This tells us model isn't missing any major relationships. So and here's a nice bonus: random forest gives us feature importance. Temperature and vacuums are clearly the most influential feature, which matches both our earlier analysis and real world expectation. It's always reassuring when the model's insights align with the domain knowledge. So um, really, to wrap it up, the random forest model performed the best overall. It explained over 96% of the variance, had very low error predictions, Temperature and vacuum are key drivers of the output, power output. The ensemble models clearly outperformed those linear ones that we have done before. And if this was a real deployment scenario, I would recommend using the random forest model, and build a real-time prediction system around it. Monitoring temperature, vacuum closely could also help optimize plant performance. This was pretty much it from my side. Thank you, everyone. I hope you have enjoyed the walkthrough. And this project was a great example how machine learning can bring value to the energy systems. Thanks, everyone.